If I go too fast, please tell me to slow down, because I like to talk fast, but I will talk slow. Okay, so today, let's see, last week we learned about aerogels and a lot about how they are made and some of the chemistry behind them and some of the different types of aerogels that you can make. And so this week I'm going to talk about properties and characterization. So I showed this slide before. This is the thing that makes aerogels so interesting in a lot of different applications. This is for silica aerogel, but again, the density is very low, from 0.003 to about 0.2 grams per centimeter cube, and again, commonly around 0.1 gram per centimeter cube. So very low density. Porosity, which is a property I'll talk about today, typically 95% air. The size of the pores, so aerogel is a nanoporous material, and the pores are 10 to 30 nanometers, and there's a distribution, and I'm going to talk today about what that is. I'll spend a bit of time talking about porous materials and then talking about how we make the measurement of those pore sizes. And particle diameters, that's the cluster, in this case, of the silica. Depending on how you make them, can be from 1 to 300 nanometers, and I will show you some of our measurements of that. Specific surface area, again, is a lot of area and a small amount of aerogel. A little bit of aerogel could cover, in the United States, we use the example of a football field, but our football fields are different from your football fields. Maybe, I don't know how big a soccer or European football field is, but anyways, it can cover a large field that people are playing on. And we'll get into down here, these things, Young modulus and shear modulus have to do with aerogel strength. And I will get into that tomorrow. I won't cover that today. And so we'll talk a little bit about the strength. This does not have information on thermal properties, but I will also talk about thermal properties tomorrow. So again, these properties we care about, why do we care about them? Kind of illustrated here. We care about the density. We care about transmission here. We mean light transmission. How much of the light passes through, and that's important for window applications and for solar panel type applications. We care about the surface area that's contained in this. And this is cylinder is meant to be an aerogel because we used to make them in that shape. Surface area is important for chemical sensing, which is an application, and is important for catalysis, which is another application. We care about thermal conductivity, particularly what's attractive about aerogels is their low thermal conductivity. So they can be used in insulating systems, and I'll talk about that more next week. And then this pore size. What is the size of the pores? What is the pore volume is important for gas diffusion, the catalysis applications. So for properties and characterization, today I'm going to talk about microstructural properties and hopefully get into some of the imaging methods at the end. And then tomorrow I'm going to talk about mechanical properties, how strong they are and how we characterize that, spectroscopic properties, and thermal properties. This is a great reference on aerogels. I don't know if you guys have a copy of this. It's the Aerogels Handbook. It came out in 2011. And there's a new version due out any day, but they've said that for about 2 years. But I think they officially said it'll be out this year, which has a lot of information on aerogels in there. And in fact, this particular slide is from a chapter on structural characterization of aerogels in the handbook by Gundrid Reichenauer. And it just goes through some of the things that you might want to measure across the top. Things like solid and void fraction, pore size, backbone size, that's the solid part. Pore connectivity, how are they connected? Backbone connectivity, how is that solid material connected? Interfacial characteristics and backbone composition and structure. So all these things, and goes through sort of the different instruments you could use to do those things. So we'll talk about porosity and density, how to do that. That's fairly simple. Then we'll talk about how to do pore size distributions, and for that we use gas sorption systems. And then looking at things, you would do some sort of imaging technique, scanning electron microscope or tunneling electron microscope or an atomic force microscope. And I'm going to show you some pictures of all of those kinds of techniques and what you get from that. And then there's some other things where we can do some trying to understand strength here. You can try to understand composition using X-ray diffraction or energy dispersive X-ray, and I'll show you some of that. So this is just a good reference for the different ways of characterizing and measuring structural properties of aerogel materials. Okay, so to start out, I'm going to talk about porosity in porous. My slide is cut off at the top. Sorry. Porous material and how we characterize it. And so we have to talk about first about the types of pores. And you can have, as an image shown here, where the dark part is the solid material, and the white part are the different pores you might have in that material. And so we can have closed pores, as in what's seen here at A, right? It's not accessible to outside of this material. And here's some more closed pores. So they are completely surrounded by solid material, and they will influence properties like density or strength or conductivity, but they're not active in processes with fluid flow or gas absorption, because the fluid cannot get to that pore if it's completely closed. And of course, this is a two-dimensional representation of a three-dimensional structure or material. So then we also have open pores, and these are shown by these various pores here that are open to the surrounding around it. And those are, as again, classifying pores as either closed pores or open pores. The open pores communicate with the external surfaces, and the closed pores do not. So we can also talk about things like dead-end pores. So they're only open at one end. So here's a dead-end pore, and here's another dead-end pore. So they're just open at one end. So again, if you have gas diffusion or fluid flow, it can't get through. It dead ends, stops. And then we have through pores, like this one here, E, goes all the way through the material. And again, you can have gas diffusion through that. It doesn't necessarily dead end, as it does in the case of this or this kind of pore. Okay, so again, dead end pores are only open at one end, and through pores are open at two ends. Another way to classify pores is by their shape. So they can be cylindrical and sort of, oh, this is sort of an, so C is this long pore here. They're open and cylindrical in shape, and A might be cylindrical in shape, but it's blind, it's a closed pore. They can be ink bottle shaped, as in B. So it's hard to see, but at the top, B is open, and it looks like a bottle. So it has a neck here, and then a bottle shape. They could be funnel shaped, like D, right? It's a funnel, it's wide here, and then it gets more narrow as you go in. And they could be slit shaped, maybe a bit like F, just a little slit. So there are many different shapes to these pores, and this makes it difficult to sort of quantify pores. So it's important to understand the different types of pores, the shapes, whether they're open or closed. If they're open, are they dead end or are they through pores? Okay, so when you talk about this one, no, I got that. Okay, when you talk about porous media, there are two primary. There's many definitions of density, and I had a whole table, but I decided not to show it to you because it's a lot of words. The two that are most important with the porous media, as in the aerogels, what we do is we talk about bulk density. And in that case, in the porous material, the pore spaces are included in the volume. And I'll give some examples, but so I've got these pores, but they are going to be part of the volume. And that's my bulk density. Skeletal density is the ratio of the mass of the solid material to the sum of the volumes of the solid material in the closed or blind pores. So then when I do skeletal, I'm only going to look at the solid material to get skeletal. So with aerogels, we do both bulk and skeletal density. If you have a powder, it's a little harder to get that density. So there's also something called tact density, which is the ratio of the mass of powder to the volume occupied by the powder after. And physically, you're tapping it. You're taking something and you're tapping it down to try to fill the spaces. So in order to calculate density, we need to know volume and mass. And again, I'm sure that this is obvious to you, but I'm talking more about what happens with porous materials. So there are a number of different types of volumes that we can define. And so if we have a powder or particles that maybe look like this in a container. So porous particle, these are porous particles and they're in a container. And this sort of shows you the bulk volume of that. We can measure this whole volume, and I'll show you that on the next slide. But then we've also got, in these particles, we have voids. So there's no solid material there. And then if we look at an individual particle here, it can contain both open and closed pores. Okay, and we can draw an envelope around that, and some people measure the envelope density, so we can get that volume or that envelope. But even the envelope will have voids included in it. All right, if we have some spaces in there. So if we look at that container containing our particles, we can define a bunch of different volumes. And so this first picture here, so this would be the bulk volume, right? I would just take this whole volume of the entire container, and I would calculate a bulk density using a bulk volume, but that would include sort of all of these voids in the picture. So if instead we look at a particle shown here, which this is this particle, we could use the envelope volume, right? The volume of that particle that we can draw. We could instead use the apparent or skeletal volume, and that's this whole volume minus the volume of any of the open pores. So if we go back here, we see here, you can sort of identify where it's showing these open pores. So my skeletal volume is what I see as just the solid left over, and I'm subtracting out the volume due to these open pores in that material. The true or absolute volume is the volume within this envelope minus all of the open pores and minus all of the closed pores. Okay, because we do have closed pores in here that we don't see, and those are those pores like this. Okay, so in that last picture, we're just identifying the actual solid material. So depending on what you, so again, for density, you need the mass of the material and you need the volume of the material. And the mass is relatively straightforward to determine, but the volume is less straightforward to determine when you have these porous structures. So depending on how you define the volume will affect the density that you are measuring and reporting. So measuring bulk density is pretty easy if you have sort of uniform shapes, right? So if you have a regular uniform shape, and this is a cylindrical aerogel from the front, and then you can see a side view, it's very easy to calculate the, assuming everything is smooth and flat surfaces, it can be very easy to calculate the volume because it's just the volume of the cylinder. And I can weigh it to get its mass, and I can simply calculate my bulk density by dividing the mass by the volume. And that's what we do a lot of in the lab. If you have irregular shapes like this, it's a little harder. There are instruments to estimate that for you. You can use Archimedes, not so easy to use with an aerogel. Because you can measure displacement of a material. It's hard to do in water with an aerogel, but there are other ways of doing that with like a sand. And then if you have a powder, and these are some pictures of catalytic aerogels that we make. This is a aerogel made with cobalt, and this is an aerogel made with nickel in it. I think their backbone on both is alumina. So cobalt alumina, nickel alumina. And we do not make monoliths when we make these. So to estimate density, we have to use the TAP method, where we will mass out, measure the mass of the material, and then use a graduated cylinder of some sort and tap, tap, tap till we sort of pack it as best we can until it settles. This is not a very good way of measuring density because it includes in that volume the volume of the spaces that aren't filled by the particles or the powders. If you have a fine powder, it works well, but if you have, these are on the order of 5 millimeters, the size of these things. So they don't pack completely with that. So you tend to overestimate the volume, which means that you underestimate the density a little bit when you do that. So for a silica aerogel, again, most of the materials we work with, and I showed you this on the very first slide, the density, this should be the bulk density, is typically around 0.1 grams per centimeter cubed. The typical silica aerogel density. Let me see. Any questions on anything yet? Just stop for a second. I think
Actually, yes.
Okay.
Because, okay, now you are talking about the bulk density of the silica aerogel, but maybe I have just to wait. But what about the skeleton density of a nanomaterial?
Well,
material.
That's coming next. I'm about to talk about skeleton. Yes,
okay,
that's next.
Thank you.
Yes. Is there another question?
I would just I would like to know, I've understood that in some way the pore structure will change the properties of the aerogel.
Yes.
But I would like to know if you can choose the porosity, if you have the open pores, the closed pores, while you are making the aerogel with the
So
conditions.
yes, somewhat. You can control that. You can certainly control the amount. You control the density and the pore volume to some degree. And in some cases, people do some very carefully templating to control the pore sizes. In the silica aerogels, not so much. We can't really control. Well, I'm going to talk about the pore size distribution in a little bit, and I will talk about how you can do some things to change that. So there is some work in trying to control some of that.
Okay, thank you. And of course the pore structure will change something like the thermal properties.
Absolutely, yes, and that's why I'm starting with the pore structure, because when I get to thermal properties,
It's
I'll help
important.
that. Yeah. So
Okay.
here's the next slide, which is on skeletal density.
May I add
so,
one more?
Oh yes, sorry.
Yeah, great, thank you. Because I know that actually, okay, porosity and density are mainly average values of the material, but porosity is homogeneous or isotropic in the layer of aerogel. I mean, if you work on what's going on in a layer of the material, so you have got an average porosity on that layer of the material. What's going on if I got a thicker piece of aerogel rather than a smaller piece of aerogel?
So most of the silica we considered to be fairly homogeneous throughout, but depending on how you make it, you can see differences in density across an aerogel sample. And particularly with when you make an aerogel in a container, like for the rapid supercritical extraction, we make it in a mold, and the supercritical fluid escapes from the top. And so depending on how big that aerogel is, you could have density differences across the material. So I didn't talk about it, but there was a study that was done on one of the rapid methods where they use acoustics, actually ultrasonics, to measure that difference across a layer. Not across the, across the monolith from sort of top to bottom. So you can get some changes, but these, right, porosity and density are bulk sort of average properties.
Okay.
Yeah.
Okay. Thank you very much.
Yes. Any other questions? Okay. Okay. So skeletal density is the other property that's important. And to measure that, you use a device called a pycnometer. So I guess pyc means dense. So dense meter is pycnometer. And it operates by detecting a pressure change resulting from displacement of a gas by a solid object. So this is we have one of these in our lab, a pycnometer. And inside, I'll get into a little more detail. It has a sample chamber and a reference chamber. It's fairly simple to use. So the idea is we have my sample chamber here has a sealed lid, and you measure the pressure in the sample chamber. And so you put an object of known mass. So here's your sample, but we don't know the volume. So we place it in this sample chamber, but we know the volume of the sample chamber. So again, the object has a known mass M, an unknown volume Vx, and it goes into a sample chamber of known volume Vs. So we know this volume, we know this mass, we don't know what this volume is because it's porous. right? So we're trying to get the actual true volume. So the system is sealed and the sample chamber pressure is measured, PS. So that's pressure in the sample chamber. So then we have a reference chamber with a known volume, VR, and that's charged to some pressure, PR, for reference pressure, which is greater than the sample chamber pressure. And once that settles, we then open the valve and let the system equilibrate. And the idea is the gas that's in here, and usually we use helium for this. The gas in here, because this is at a higher pressure, will move into here and will infiltrate into your sample if it's porous. And so then using the gas law, we can determine the volume of the sample, right? So pressure times volume equals number of moles times the gas constant times the temperature. And so initially we have the pressure in the sample chamber times the volume, which is the volume of the sample chamber minus this unknown volume, plus the pressure in the reference chamber times the volume in the reference chamber. And then once we open that up, the valve is open, we have this new pressure, right? The system equalizes to a new pressure. And now that pressure times the volume is now the reference chamber, the sample chamber minus whatever is in my sample. And so then we can just equate these two sides. So this, it's all still the same number of moles, and this is done isothermally. The same number of moles. So we then equate that and we can solve now for the unknown volume, right? So it's related to the pressure in the system after it reaches equilibrium times the sample chamber volume plus the pressure in the system times the reference chamber volume minus the initial sample chamber pressure and the initial reference pressure, both times their volume. And so this way we can calculate what that actual volume is. And it takes a while to do this. You know, you have to wait for the system to equilibrate and for the reference chamber pressure to infiltrate into that sample. But once you get that, so pycnometer measures the volume. And again, it's going to measure, it's obviously not going to measure the volume of any of the closed pores. It's only going to be able to get that open part. And going back to this, right? This is what it's able to determine, this volume. They can't do this. They get this volume. So once we do that, we can then get density, and this is what we call skeletal density, is equal to the mass that you originally measured divided by the volume that we've just measured it using the pycnometer. And so for silica aerogel, the skeletal density should be around the density of silica itself, which is somewhere around 2 grams per centimeter cubed. We've made these measurements and we get something a little lower than that, but that's just saying that we're still overestimating the volume because we don't have access to closed pores. So it's almost an indication of how much of the space is occupied by closed pores. And so that's the technique for measuring skeletal density. Any questions on that? Pier Giovanni, you had asked about it.
Oh, really? Thank you.
Okay, fairly simple to do. Oh, my slides are a little odd today. All right, so porosity then.
So sorry, Just to add now, well, I was thinking about one thing. Okay, so you said that actually, okay, perfect. The skeleton density is actually equal to the density of aerogel itself, or better, to the silica
Yes.
density itself. But the point is that, okay, we know what is the upper limit, because
Yes.
it cannot be more. But the problem is that we cannot exactly know what is the right density because we are overestimating the volume at the end. So,
Yes.
okay, we know what is the upper limit of the density, but we know exactly what is the real density, or we can just say that, okay, approximately we are very close to the real results if we refer to the silica density.
I think, yeah, so what I think the measurement you make is indicating something about the volume of closed pores, right? Now, and also the silica, depending on what you do with the, if it sinters a little bit, it's going to be, if you heat it, it's going to be a little different, right? It's going to be a little denser. So we know the upper limit, we know what we measure, and what you measure can tell you something, I think, about closed pores in there. What percentage is closed in the system. Does that answer?
Okay, perfect.
Okay, so porosity again is like an average. There's different ways to measure, but one of the simplest ways is this average value, and it's the fraction of the apparent volume of the sample which is in the pores. So it's the volume of the pores divided by the apparent volume. And so what is reported depends on the method used to calculate that. So you just need to pay attention to what's being reported. So the pore volume is either that of the open pores, so it would be an open porosity, or that of the closed pores, which would be closed porosity, or that of both, which is total porosity, which is usually what we do because we don't necessarily know the closed pores. So you can calculate it using the bulk and the skeletal density. So that porosity, because this is related to the volume of the pores, is just 1 minus the bulk density over the skeletal density. So for a silica aerogel, if you have a skeletal density of about 2.3 and a bulk of about 0.08, that's why the porosity is so high. That would give you one of 97%. So depending on your conditions, people report 90 to 99%, depending on how that aerogel was made, what is the resulting bulk density and skeletal density. So that is a simple way to estimate porosity, but it is, again, an average way of doing that. So now I'm going to talk a little about porosymmetry. So what I just talked about was kind of average values of density and porosity that we can get. And I talked about the difference between bulk and skeletal. Now I'm going to talk about ways to actually measure pore size. Okay, so it's a pretty important property. It is hard to measure because it's people can make materials with, perfectly cylindrical pores and things like that, but aerogels aren't like that. The shape is highly irregular. So how do you define size depending on shape? And then the other problem is they're usually interconnected networks. And so what is reported may depend on the way in which pores are encountered and the method used. So porosymmetry is an analytical technique that we use to determine information about porous structure, such as pore diameter, total pore volume, surface area, and bulk and absolute density. So we use it for that. And what it does is it involves the intrusion of a non-wetting liquid, or gas is what we use, at high pressure into a material by using what's called a porosimeter. So pore shape and size, so it's difficult, again, to know what the shape is. They're often described as cylinders, prisms, cavities and windows, slits, or spheres. And I showed in one of those earlier slides some examples of the different shapes. And so when you're describing a porous solid, it's complicated because you have the different shapes of pores in the same material, right? You have connection between pores, which may vary in size, shape, and location. And you have a distribution in the size of the pores. So I have, again, going back to the original picture, right? These are sort of different pores, but they're connected in various ways. They're different size distributions. Obviously, some of them are inaccessible to these sort of techniques. And they have different shapes. So when you use a porosity system, you end up having to choose a general shape for these. And so there's been a lot of work in this, and they talk about things like connectivity. How are they connected? Tortuosity, how the pores are winding, connected, and then do they dead end? Things like that. And then there's been some work with fractal geometry in describing pores. The main takeaway is there's an organization called the International Union of Pure Applied Chemistry, IUPAC. They have some, and I've got the references here. They have excellent references on measuring pore size distributions. But their official definition of the pores are those that are smaller than 2 nanometers in size, and they usually use like a diameter or a width. Again, it depends on the shape. But they have a size smaller than 2 nanometers. Those are called micropores. Pores with diameters between 2 and 50 nanometers are called mesopores. And then pores that are larger than 50 nanometers are called macropores. And so one of the things, I just talked about estimating pore volume using skeletal and bulk density. We can also, we'll see, use a porosimetry system to measure pore volume, but it doesn't measure all of the pore volume because they work in this range. They work with the mesopore, and you can estimate the micropores too. But so the method used for this is gas or vapor adsorption, and so a gas, and usually nitrogen is used, at its boiling point is adsorbed onto a solid sample. Okay, so here's a layer of my solid, and I have my gas that will adsorb onto the surface. And the amount of gas adsorbed will depend on the size of the pores in the sample and on the partial pressure of the gas relative to its saturation pressure. So gas adsorption is a technique that measures the amount of sets at different pressure settings. It is able to determine how much gas is adsorbed onto a surface. And so from that, you can get two important things. One is the surface area, and I'll go into some detail about how that is done. The surface area is determined by calculating the volume of the first layer of the gas on that solid. And it is used, it's called the Brunauer, Emmett, and Teller, or BET equation, which gives a specific surface area of the material. And so people often talk about the BET surface area, and I'll go through that calculation. You can also get the pore size distribution. And so as you go to higher partial pressures, and so what I mean by the partial pressure is we pressurize the system, we measure that, and we go all the way up to the saturation pressure. And you get, you go through a procedure of adsorption, where you're depositing the gas onto the surface and into the pores, and desorption, where you're pulling the gas off of it. And these things are measured at constant temperature, so they're called isotherms. And based on that, the Kelvin equation, or the Barrett-Joyner-Hollanda equation, which I will not go into great detail on, but it can be used to calculate pore size distribution. It tells us how many pores, or what volume of pores are in each size range. And from that, you can get things like the average pore volume in there. So this is a powerful technique for doing this. I hinted at that they're generally applicable, so the gas adsorption methods are applicable in the mesoporous range. So when you use it, we're only going to get the pore volume of pores that are between 2 and 50 to 100 nanometers, something like that. There are techniques to use the information we acquire to calculate the microporosity, to figure out how many pores are less than 2 nanometers. I won't talk much about that, but you can't really use it for macropores. So some of the first studies we did, we got pore volume, and then we went and we calculated porosity, and there's missing pores, and that's because we can't really estimate the macro pore size. There are techniques for doing that, and one is mercury porosity. So instead of having the gas absorb, you use mercury, and mercury is capable of measuring the macropores, the large ones. But we can't use it for aerogels because they can't take the forces that are encountered. They'll just cause it to collapse. There are some other methods, small angle X-ray scattering methods. I don't use this, so I don't know much about it, but there are other techniques for estimating those. And then people have done some NMR. I will show you some electron microscopy where you take images of the structure. I'll also show you some atomic force microscopy. So you can also try to learn some information from these other methods. But by far the most common one is the gas adsorption methods. So this is a gas adsorption system. This is one we have in our lab. This one is made by a company called Micromeridics. It's called the ASAP 2020. ASAP stands for Accelerated Surface Area and Porosimetry System. And so just sort of briefly how you do it, and then I'll get into more detail on it. But basically, if you're going to use this system, you crush your material. So you don't put a whole aerogel in there, you crush it into a powder. You have to crush it carefully. You don't want to change the pore structure. And I'll show you some results of compressing an aerogel too much on that. And then you also, depending on the size of the material, will affect your results. So, and I'll also show you some of that. And then you have to degas your sample, and that's to drive off anything that may have adsorbed already onto the surface, like water vapor, if the sample's been sitting out. And so this is a degas port. And so these are tubes, and you put your sample in the tube, and this is connected to a vacuum pump. Okay, so it's evacuating the sample, and there's it's called a seal frit, a cover, so that sample doesn't, get pulled up. These are heating mantles, so they heat the sample slightly. And so you heat the sample, and as you heat it, you drive off whatever is on there through the vacuum pump. And so we tend to do this 6 hours of this to degas our sample. And then you run your adsorption and your desorption test. And so that's done over here. This is a container of liquid nitrogen, which is used in the degassing to cool the vacuum evacuated. So this is a container of liquid nitrogen. Your sample goes on here. The system is connected to a bottle of gaseous nitrogen, which is then dosed. You add a known volume of gas, and then you measure, it's not shown here, but there is something to measure the pressure. Actually, sorry, it's up here, to measure the pressure of the sample. And so you run what's called an adsorption test and then a desorption test. So adsorption is adding the material, desorption is pulling it off. And so there are some key parameters when you do a test like that. And one is the number of points means number of pressures. We do many measurements, 60 or 70 points. And then the other thing that's really important with aerogels is something called the equilibration time. The way the system works is it doses, it adds some gaseous liquid nitrogen, and then it waits for the system to equilibrate, as in it's adsorbing onto the material. And when it's all what you actually set is the partial pressure you want, and it keeps adding a quantity of gas until you get to that pressure. But you have to wait. You have to have enough time at each point to make sure that it's equilibrated. And because aerogels are so nanoporous, this can take a long time. So for us to run an aerogel test takes over 72 hours because of this equilibration time. Other materials, it's not so important, but aerogels, it is important in that. Okay, so I'm gonna do a couple more slides. I'll stop for questions and then we'll take a break. But so again, here's an image of what's going on from, and this is adapted from this company Micromeridics. We call it an aerogel here though. So as you're adding the gaseous liquid nitrogen, it starts to condense. Right? It doesn't condense. Sorry, it initially adsorbs in isolated places on the surface. Right. So here's my aerogel surface. These are some pores. And at some point, you reach what's called the monolayer, where you have one layer of the gas on the surface of the material. And that's where what we use, that information is what allows us to calculate surface area, right? And I'll show you that in a little bit, but it's that whole area. And then we keep adding more material, and you start to go to multi-layer filling, okay, where you're filling more and more of the pores. And then eventually you have this condensation where all of the pores are filled. And from that, we can figure out pore size, pore volume, and distribution. Okay, so adsorption, and the opposite is the desorption, is when we start to pull the adsorbed gas off of the material. And so what's used is a phrase called the isotherm, which is the quantity of gas that gets adsorbed at constant temperature as a function of gas pressure. And do I have one? Yes. And so here is an example of an isotherm. This is actually 3 isotherms. So this plot is the volume adsorbed or desorbed versus the partial pressure. Okay, and this is just showing the upper range of partial pressures. And this is from the aerogels handbook. This is a silica, this is a rather dense silica aerogel. That's density is pretty high. And this is an example of what happens with equilibration time. So let me explain one. Let's look at, let's look at the red. So the red, you are adsorbing more and more, as you do this, the material goes up. The pressure goes up. Okay, and when you get to these high pressures, you start to adsorb even more. And then this is the desorption curve. It goes down. And this is something called hysteresis. I'll talk about that in a minute. But this test, what this plot is showing is they did a 70-hour test and they got the red. They did a 24-hour test and they got the blue. They did a 19-hour test and they got the gray. And it is very, you will get very different results on the pore volume and the pore distribution just by looking at these differences. So this is, and the way they control this is that equilibration time. So that is a very important thing. I'm going to talk about, okay. I'm going to stop now and see if you have any questions, and then we'll take a break, and then I'll get more into what these distributions mean. Any questions?
I got just one, maybe trivial, but let's say that the point is that what is the thickness of the first layer of gas when we are trying to measure the surface of the silica aerogel?
So it's related to whatever gas you use. So it's the size of the gas molecules. And so that comes, and I will go through the calculation of that and I'll show you that.
Okay.
Yes.
Okay. So it depends. Yeah, really. It's the first layer of the molecules of gases itself.
Yes. So,
okay.
I mean, the thing is, how do you know when you have the first layer? But they've done some work to determine that. It occurs at certain partial pressures. And I will do that calculation with that. Any other questions? Anything else?
I have a question, but I think that the problem is I missed something for sure.
Tell me.
You told us that you use the liquid nitrogen for this measurement. Is that true? And there are no problems with the frozen at all, with freezing the sample?
No, so no? Let me go back. Okay. You have a tube with your sample. The material is not in contact with it. It just, what it provides is an isothermal condition.
Okay.
Right, and so the sample's in a tube here. We deposit in gaseous liquid nitrogen. Now, of course, it's going to condense, and that is what happens. But there's no problem with harming the sample.
Okay. Thank you.
Yeah, good question. Okay, let's take how about 11:15? We'll start again. Okay. So about 11 minutes. Okay. I'll see you. Okay. All right. Bye-bye.
Thank you. Bye.
Okay, we'll start again. Go back here. Can you see the screen okay and hear me?
Sorry, I didn't get the question. I was away.
Just making sure. Can you hear me and see the screen?
Yeah.
Okay. Okay, good. Okay. So we left off with this equilibration, but I want to talk about what this isotherm looks like for a silica aerogel. I'm going to show a lot of plots that will look like this. This is the amount of the gas that was absorbed. This is the relative pressure. Okay, that's the saturation pressure, P0. So as you go from very low all the way up to saturation pressure, and they've got that. I don't usually have the top thing. So, sorry, the isotherm represents, this is each point. At each partial pressure, we measure the amount of the gas adsorbed. And so we call it an isotherm because it's all, in the case of liquid nitrogen, it's at 77 degrees Kelvin. And so this is a point, each one of these points. And what you have is this is the adsorption branch. Okay, that's where you're adding material. And this is the desorption branch. Okay, so some things about this. So this is typical for a silica aerogel. Down here in this region is where you are filling sort of micropores. And this information tells you something about the micropores. Hold on, I think I have. Okay. This area in here.
Maybe it's just my problem, but I cannot hear anything.
You cannot hear? Can others hear?
Yeah, I can. I can hear.
Okay. Who can't hear? Who was it?
Pier Giovanni can't.
Pier Giovanni, you should.
But I think he.
I think it is his.
Yeah, he can't. He can't hear me too.
Let's see. You can send him a note. No, I can't. Pier Giovanni, can you hear now?
No.
No.
I try to send him a message via WhatsApp.
Oh yeah, send him a message and see. I can't seem to message on this. Tell him to let us know when he can hear.
Yes.
Yeah, okay, great. Solved.
You can hear now?
Yeah. I don't know why or how it could be possible that I got that you are muted right now. I can hear you anyway. So okay. Great.
Okay. So what I'll say again, so what I was saying is this is a typical isotherm. So isotherm is what we call the data we get from a gas adsorption test, because it's all taken at the temperature of liquid nitrogen. And so these plots show the amount of the nitrogen, again, that comes in as a gas that gets adsorbed or desorbed. So that's just a volume versus the partial pressure. Okay, partial relative to the saturation pressure. And so each one of these points is a test. And this one is adsorption. This is when I'm adding the gas. This is what I measure when I add the gas. But when I take it off, I measure this. And that's called the desorption isotherm. So adsorption and desorption. And so it turns out, and I'll get into more detail, that we learn things about micropores, again, less than 2 nanometers around here. We learn things about the surface area in this range. This is where you have a single layer. And then we learn things about the mesopores in this area. Okay, so this information, this is the data you take, and now we want to transfer it into, convert it, calculate some more interesting information from it. So there are classifications by that International Union of Physical and Applied Chemists that have come up with classification of these isotherms, different types. So types of physisorption isotherms. And so you might have something that looks like this. So again, this is amount adsorbed, and on the horizontal and all of these is the relative pressure. So if you study a material and it looks like this, very steep and kind of flat, this is a microporous material. Okay. So you don't have mesopores, you only have micropores in something like this. This type 2 and 3 are multi-layer adsorption on materials. We don't use these ones so much. Type 4 and 5 are relevant for the studies we do on aerogels, because they have what's called this hysteresis loop, right? So on these, the adsorption, desorption are the same. On type 4, my adsorption is different from my desorption. Same with type 5, and the difference are wetting and non-wetting. And then this is this type 6 is stepwise, which you see in highly ordered materials. So this is what we see in aerogel materials. Actually, this is the one we see, and it's evidence of this capillary condensation. And because of this, we have mesopores. The other thing, this hysteresis, where there's the difference between adsorption and desorption, so we call that hysteresis. And this is the reference to the IUPAC document. They define them, and looking at these, we can tell something about the material. So this type of hysteresis is often associated with porous materials. That they know from other methods that they have kind of agglomeration or agglomerates or a bunch of uniform spheres with a narrow distribution of pore size. And in fact, that is actually what we see with the aerogels. And these other are seen for different types of materials. So you can, in addition to learning something about your material based on the shape of this curve, you can learn something based on the shape of the hysteresis. And so this reference, they have a very good, this is sort of the standard for looking at the isotherms. So let's go back to the aerogel, silica aerogel isotherm plot. Again, volume versus pressure. And so let's look at this area here. So if it's steep in here, it means you have micropores. Okay, so this is not very steep, it's a little bit steep. So there's probably some micropores there versus straight. Then this slope here is related to the surface area. The higher the slope, the higher the surface area. So if it went like that, it would have a higher surface area than something that goes like that. So you can tell a lot just by looking at the isotherm, you can tell a lot about the material. And we're going to do that. And then I'm going to show you the methods to actually get quantitative data. So right now we're just looking at the isotherm. Then the hysteresis, if you have hysteresis, you have mesopores, okay? And the position of where this occurs is related to the size of the mesopores. So if the hysteresis occurs over here, in this area, you would have smaller mesopores than if it occurs over here. So if you're comparing different samples, you would see that difference. So we can tell a lot just by looking at this behavior. And then we can tell something about how high this is. So the total accessible porosity in the micropore and the mesopore range is estimated from how high this is, right? How much gas is adsorbed on that surface is relative to that. Okay, don't forget there are also macropores, but this does not measure macropore size. So again, if there's no hysteresis, we don't have mesopores, we're just macropores. Again, remember, mesopores are 2 to 50 nanometers. Okay, so that's just qualitative. Any questions on the isotherms?
No.
The shape is very important. No? Okay. So that is good, and we can just look at isotherms, but we want to get some more quantitative data. We actually want to know how many pores are in each size range. And so there are some different theories that you can use to determine the micropores. They use something called density functional theory. I don't use that. And there's Dubin and Radushkevich for the micropores. Our materials are not particularly microporous, so we don't do much with them. The two things that for the aerogels we look at, we're most interested in, is this Brunauer-Emmett-Teller, the BET theory, which describes physical adsorption of gas molecules on a solid surface, and from it we calculate surface area, and I will show you that calculation. And then the Barrett-Joyner-Helenda, the BJH theory. So that extends BET and gets into interactions between the condensate and the material. And from that, you can figure out the pore diameter, the pore volume, and the distribution. And I won't go through that theory, it's more complicated. But I will do the BET because it's reasonably simple. Okay, so BET, it describes the Brunauer-Emmett-Teller equation, describes the relationship between the number of gas molecules adsorbed at a given relative pressure, and it's used to derive the surface area from that isotherm data. And so the monolayer, so this again, here's my surface. I start with a layer of gas that covers the entire surface. So that's the first layer. And then we add on more, but we're interested in the monolayer. So their equation, which they derived based on adsorption theory, is that the monolayer absorbed gas, what should be adsorbed gas volume, so VM, this quantity, I want to know what that is. I want to know the volume of gas it takes to cover the whole surface, because then knowing information about the gas and the size of the molecules, I can then determine what the surface area is. So there is a relationship between the monolayer adsorbed gas volume and at every single, so we have every point on the isotherm represents an adsorbed gas quantity and a pressure. So for every point here, at each of these points, I have how much was adsorbed and what is the pressure. So at each point, they show that they are related in this way. So that's the adsorbed gas quantity from the isotherm. P0 is the saturation pressure of the adsorbed. P is the equilibrium pressure. That's the thing we measure. C is something called the BET constant. It's related to the heat of adsorption for the first layer and the heat of vaporization, as well as the gas constant and the temperature. So it is calculated when you do an analysis. And so this sort of relationship exists. This is the thing we want to determine right here, using this information from the BET equation. So the way it's done, if you look at that equation, right, this is like an equation of a line, right? This is y, this is the slope, this is x, and this is the intercept. Okay, so we plot it to determine the so we plot it, and from that, we can determine, so if we draw this line, we can fit the line, and we can determine what the slope of the line is and what the intercept here is. And from that, we can calculate C and VM. Again, that's the volume for one layer of gas to be adsorbed. So it's fairly simple to do. So what we do is use only the low pressure part. So you can only have this linear BET equation showed this, that you only have this linear region for partial pressures between 0.05 and 0.3. Okay, below 0.05 is where you are microporous. Above 0.3, you start to add additional layers onto the surface. So they've identified this region where you have a linear region. And so typically you would take some 5 points in this region. You can use as many as you like. And you fit that data. You plot it this way, right? This is something I measure. This is something I measure. This is something I measure. You plot it and you fit an equation of a line. And so the slope of that line is related to this. The intercept is related to that, and you can solve. So the volume of the monolayer is just 1 over the slope plus the intercept, and this BET constant is 1 plus the slope over the intercept. And so when you do an analysis, you need to look at this to make sure it is a reasonable number, to make sure you had a good fit. And you also determine how good a fit you have when you look at the data to get that. So once you get that, so now I have my volume of material. Now I can figure out the total and specific surface area. So the total surface area is equal to the monolayer gas volume divided by the molar volume of the absorbed gas. So that will depend on the gas used. So in our case, we use nitrogen. So I have volume, and this gives me the moles. Oops. That will give me the moles of gas times Avogadro's numbers, give me the number of molecules, and the cross-sectional area of the adsorbed gas molecule. So it tells me how many gas molecules there are times the area, times the cross-sectional area, gives me the total surface area of that sample. And so what is typically reported is a specific surface area. So you would divide that by the mass of your sample, and that results in something in meters squared per gram. So that tells you how many meters squared of area there is per gram of sample. Is that clear? Any questions on that?
Yes, it's clear. I would just like to know a pragmatical question. And I'm not sure if it's the name of the instrument or it's just the name of the equation, but
Yes.
the BET,
Yes.
how much it's gonna cost?
That costs
Instrument.
nothing because that's the equation.
Yes, of course. I get it.
The instrument is called the gas adsorption system.
Okay.
So there's a range of prices. I mean, I think our system was about $30,000. It's not, they're not inexpensive. They are expensive to do.
Okay.
They have other systems that do not cost as much. And it is also possible, you know, there are companies that do tests for you, that own these and will test materials to do something like that. But the BET, that just means the BET.
The three names of the people.
The people who developed the theory, and that theory is used to calculate surface area.
Yeah. I see before Bennett, Edmond, and something else.
Yeah.
You showed us the name.
Yep. It's just their names. So you can use that for free. But to get the data, you have to have an instrument like a gas absorption system to get that.
Okay. And I was asking this because, of course, you can use this also for check how much CO2 a material is going to absorb, right?
Yes, we can. Yes. Yep. Okay, so so that's surface area, and the other part is the BJH theory, which is the Barrett-Joyner-Hellenda. And again, going back to this picture, which is from the company Micromeritics that we use, it's this part here. So again, we just talked about single layer. That theory seems pretty reasonable to do that. But then when you keep increasing that gas pressure, you get more and more filling the pores, okay? So as the pressure increases, the gas condenses first in the pores with the smallest dimensions. And then as you increase pressure, you keep filling all of the pores with the liquid. Comes in as a gas, but it condenses to a liquid. And so desorption is the other way, where you reduce the gas pressure and it evaporates off the condensed gas. And so if you evaluate the adsorption and desorption branches and the hysteresis, gives you information about size, volume, area, distribution. And so the commonly used method is just called BJH. So Barrett-Joyner-Hellenda is used to determine pore volume and pore size. I don't think I have this in a slide. No, I'll go back to it. So I don't think I have it in a slide, but one of the things that is important, I told you that pores come in many sizes and many shapes. And so when you do this sort of analysis, you make an assumption about the shape of the pores. I've done some things where I assume it's cylindrical, and then maybe I assume it's spherical. Not a big difference, but it is something you're assuming. It's an approximation when you do this, but gives some good information, particularly comparatively. So I'm not going to talk about the theory other than it has to do with capillary condensation, but I'm going to basically show you some results. So this is an isotherm, volume absorbed, partial pressure, for an aerogel in black and for a zero gel in red. And remember, we talked about zero gels are not, they're collapsed aerogels. And so again, like the other one I showed you, these are silica, both of them. Like the very first, again, we see adsorption and we have a hysteresis and desorption. So the surface area information, you look down here, it's related to the slope, right? The aerogel has a surface area, in this case, it was about 830 meters squared per gram. The zero gel, still pretty high. It's a high surface area, but lower, and you can see the lower slope here. So the pore volume of the aerogel, based on this analysis, and I'll show you the BJH results in a second, was 3.4 centimeters cubed per gram. But for the zero gel, it is only 0.5 centimeters cubed per gram. Because with the zero gel, it dries, it doesn't dry supercritically, so those pores all collapse. So there's less, and again, this is only the accessible pore volume. It is much smaller in a zero gel. And you can see very different isotherms. And then if we look at, and so this is what you get from BJH analysis. You get a plot of something like this, pore volume versus pore diameter. And it is telling us sort of how many pores exist at each diameter, okay? And this is a piece of relevant information, is that this was taken from the desorption isotherm. You can do the analysis on the adsorption or the desorption. We find for the aerogels, the adsorption does not show any peak. It doesn't work very well, so we always use desorption, but it's something you have to report when you're doing that. So what BJH tells me is, where are the pores? And this is telling me I have a lot of pores in between 10 and 20 nanometers. So that's the peak. So materials with this sort of hysteresis tend to have a narrow peak like this, okay? And then I still have pores, you know, over this whole range. And this, so this aerogel, again, that's pore, the pore volume is calculated by summing up all of this area. That's how we get the pore volume. But again, it is only the pore volume in this range of diameters. Okay, so it goes out to the 100 nanometer range. It also tells you the average pore size. So for the aerogel, we had this. For the zero gel is the red. Zero gel has small pores. Okay, the average pore size is only 3 nanometers. Again, because they are collapsed. You can see much lower peak. It does not have as much area, as much volume in the pores. And so this is a typical information you would get from a BJH analysis. And this is a silica aerogel and a silica zero gel. And this is very useful to have this information. I have, I want to show you some things we did with this. We did a study on the effect of particle size. So remember I said you take the aerogel and you break it up. And so we did a study, very fine, medium, and coarse. So you can see these pieces are a centimeter. Okay, and these are very fine powder. This is a TMOS-based silica aerogel. Density is about 0.1. These had surface area of about 550 meters squared per gram, and that's affected by processing, things like that. So we wanted to see what happened when we did these tests to what we measured, because remember, you have, even though this is fine, the nanostructure is even finer. Each of these particles here has a very nanoporous structure to it. So this is an isotherm plot again. And in this case, this is the fine grain. So we broke it up very fine. And here is equilibration times. We wanted to see, I remember I showed you the plot at the beginning where they had very different isotherms based on equilibration time, or time to do the test. And so here's my adsorption on the sample, and here's my desorption. And again, it's very much a mesoporous material. We can see that. And in this case, I think the 40-second took 80 hours, 3 days to do. And the 5-second probably took a day. And you can see there is some difference, but they are fairly similar because I have a fine grain, a small powder. So the equilibration time, probably 10 seconds was fine to do that. And if I look at the coarse one, so this is the big pieces that are almost a centimeter, I have a very different result. Here is when I only wait 5 seconds, 10 seconds. The 20-second one had a problem, but up to here it looked good. And then 40 seconds. And so now we see a big difference based on the size of the pieces of material you analyze, right? It's going to take much longer for the gas to penetrate into these larger pieces than it will the smaller pieces. Now, I'm not showing the medium. The medium was similar to the fine. But, and I'll show you don't want to crush it too much. You don't want to apply a large force when you do this, because you can change the pore structure. So the way we do this is we break it gently into these small pieces. Okay, so here, let me see something. With the 40 seconds, and this is the same material, so 40 seconds on the coarse, I get above 2,500, which is similar to what I get for the fine. So it's the same material, I should get the same result. Okay, but clearly 5 seconds is not capturing what we need. So if I perform a BJH analysis on this with pore volume versus pore diameter, we can see for the fine grain, even the lower ones, what happens is you miss the peak. You miss the maximum size. So the maximum amount, what that volume is. So if you're trying to identify pore volume, total pore volume, it is very important to do it slowly. If you only want to know where the peak is, you don't have to go as slow. In this particular aerogel, right, the peak is around 22 nanometers. And most of them capture that pretty well. But they won't get the total pore volume. So with aerogel, I am always very careful about reporting on pore volume. If I want to do it, I do very, very slow tests to make sure I capture that peak. And then here's the coarse grain, and you can see the big difference between. So again, the 40-second for the fine and the coarse is very similar. Yeah, around 20 nanometers. it depends, your peak will depend on how many points you have in there. So generally within a couple nanometers you get it. But at 10 it drops, at 5 and 20 there was a problem with. But you do not penetrate enough, but you still can identify maybe the location, but just not the pore volume. So it is important to do this carefully. Okay, so I want to just finish off this section showing you some examples of things that you can do with gas absorption analysis. And so, but before I do, any questions on the BJH, on that method and what you're getting? You're applying this theory to extract from that isotherm some information about the distribution of pores. There are assumptions in there about this, the shape of the pores that are inherent in the model. But we find it very helpful, and I'll show you some examples of where we've used it. But any questions on that bit? No? Okay. How do I go back? I will, I think, finish with just some examples. So we make aerogels. These are catalytic aerogels. They are, what are these? These ones have, they're copper and aluminum, copper and alumina. So instead of silica, we make an alumina backbone, and we soak the alumina wet gel in a copper salt solution. And Mary Carroll talked a little bit about this. And that creates some copper nanoparticles in the material. And these are useful in catalytic applications. And in this application, we study automotive exhaust pollution cleanup. So we're trying to convert what comes out of the gasoline engine, the nitrogen oxides, the unburnt hydrocarbons, and the carbon dioxide into something else. So we're looking, I'll talk about this, I think, in the last week. So we're looking at how effective they are as a replacement for precious group metals like platinum and palladium, which are very expensive. So one of the things we needed to determine when we make the material, then we heat treat it, because in a car, it's going to get very hot. So we heat it up to 800 degrees C. In order for this material to be of potential use, you need to be able to slurry it. So what that means is to put the aerogel, we put it in slightly acidic water, because that's the technique that you would then take and put on a structure to put in the back of your car, you know, at your exhaust stream. So we did a study to see if we could slurry it, because we keep talking about how water destroys it. So we wanted to see what would happen if we could do it. So these are, again, the isotherms, and the blue is as prepared. Okay, again, it's got the, you see the hysteresis loop here is closer to 1, and it results in pores that are quite a bit bigger than the silica, and it's also a wide distribution. But the average is in the 40. So this is the as prepared material. Then we heat treat it to 800 degrees C. And when you do that, it densifies. So you go from a density of about 0.1 to a density of about 0.3 when you heat treat it. What also happens, so you can see here for the as prepared, has a higher slope than the others, and it has a surface area of about 330. Once I heat treat it, my surface area decreases a lot. Still good though for a catalyst. And then surprisingly, we still cannot explain this result, but after we heat treat it, we then put it in slightly acidic water, and then we let it dry, and it gets back some of the pore volume. We don't know why. It's an unexpected result. It still has a low surface area. You can see that here. It is very dense now because it's been collapsed even more, but it has more pore volume, right? And the pore volume is related to the area underneath this curve. So this was an example of where using gas adsorption and pore asymmetry was really helpful to us to learn what was happening with our materials. I have a couple more. The other thing, this is related to, we did a study where we crushed aerogels, applied forces to them, and I'll talk about this more tomorrow when I talk about structural. But we had some aerogels, these were silica, and these were as prepared, which corresponds to this one, that same sort of peak I've shown before, narrow band around 20 nanometers. And we tested those. Then we applied force or pressure to the samples. And when you do that, it crushed it and it caused some densification of the pores. And we discovered that when we did that, and these are just different amounts, right? We lose pore volume, which makes sense. And it shifts to smaller pores. Okay, it goes from 20 nanometers maybe down to 11 or 12 because we're crushing the aerogels. And this is relevant for when preparing samples for gas adsorption. You don't want to crush them. We have to be careful where you crush them. You don't want to be crushing them and applying large forces to the sample because you can change the material. And then I don't know, do I have another? Oh yeah, my last, I think this is my last, yeah, I just got to do one more. The last example I have is, we talked about making aerogels with TMOS and with TIOS. TIOS is the other starting chemical, tetraethyl orthosilicate. And so we've done a lot of work with TIOS because TIOS is significantly less expensive than TMOS. So if we could make TIOS silica aerogels, that would be good. The problem with TIOS is it's very hard to make it transparent. So we haven't been succeeded in doing that. But this is an example of a study, some work we had a chemistry student worked on trying to optimize TIOS aerogels. And so we can look at, again, pore volume, and sometimes there are different units in how they're plotted, but basically pore volume versus diameter. And in red is the TMOS ones I've been showing you at about peaking at about 20 nanometers. Well, the TIOS have a narrow band, but at a much higher average diameter, more like 40, and which is going to affect their optical properties. And so we can use this sort of technique to compare those types of aerogels. So I'm going to stop here. What I have next is some information on imaging, which I'll pick up with that tomorrow. So what I've covered here is the methods for density, porosity, and then pore asymmetry to extract information about the pore sizes. Again, there are limitations in what we can do. I talked about, open pores, closed pores, the different sort of information you can get, but it's very effective. And I tried to demonstrate with the last few slides that it's effective when you are comparing materials to try to understand what is going on. So next time I will start with imaging, which is another way we can take pictures, very hard, but at the nanoscale, to also look at the pore structure that way to get more information about it. And I have some examples of scanning electron microscope images, some tunneling electron microscope images, and then some atomic force microscope images, which will help to add to what we know about the pore structure. Okay, perfect. It is 12 o'clock. Any questions? Nope.
No.
Nope. Okay, did I go too fast at the end?